Okay, so good morning, and let's start. And so, how's your last week?
It's fast, like fast. But it's great. Good.
Yeah, same here. Yes, last week it was also a very good week for me. I got the opportunity to go to my gym 3 or 4 times. Yeah, I really enjoyed that. So yes, and I also went to visit go to see the cherry blossom. Do you know where is it? There is a park in Newark, and just search Newark cherry blossom. You'll be able to find it. So if you got some time, you should today blossom. How to spell that? And yes, the Branch Brook Park. Yeah. So it's really beautiful. And if you got some time still, you can go to visit today. It's really beautiful, and it's just the peak season. So for the flowers. Okay, so yes, have allergies. Okay, which is very sad. But since you have your mask on, so probably you can have a try. So yes, and yes, the good times go very fast. So yes, we need to come back to the lectures. Okay, so and starting from today, we're going to have the last topic in our class, and that is called graph, and it's search algorithms. So graph search algorithms, and so graph is basically a data structure, as previously I mentioned. So data structures usually come with operations, which are algorithms. So for example, if we talk about stack or queue, so these are just data structures. So because they enforce the first in and first out policy, they're literally the arrays with some buffer space. And then we learn some this is that for the data structure stack and queue, we learned a couple of operations or algorithms. We call them insertion or deletion. So something like that, deletion. And then for binary search tree, the binary search tree data structure, we learn some operations or algorithms like insertion, search, and minimum, maximum. Okay, minimum and maximum. So today we're going to learn a new data structure named the graph, and we're going to so in the next 4 weeks, in the following 4 weeks, we're going to learn quite a few algorithms or operations. So related to graph, which are something like this. Most of them are just search algorithms, but we have different preferences when we're doing the search. So we're going to learn in total 11. Here we're going to learn 11 search algorithms for graph, and so it's going to be a very tough topic with a lot of things to discuss. Okay. So then this is the outline of today. So first we're going to say what is a graph. We're going to learn what is a graph, and then we're going to learn the first algorithm in graph called breadth first search. So what is a graph? The graph is basically a set of nodes connected by a set of edges. So here you can see a graph, and also this is another graph. And here you can see that graph is pretty much similar to trees. For trees, we have this structure, a set of nodes connected by a set of edges. But for trees, they have to be layered. They have to follow a hierarchy. So we got the hierarchy. So we have the root node, and then so the second level of nodes and the leaf nodes. So this is the limitation of tree, but for graph it's pretty, the structure is pretty free. We can have any connection that we want. So this is one example of the graph. So it's more free. This is the the graph, and here you can see that with these two examples, on the top example, the edges do not there is no direction with the associated with the edge. But for the bottom example, for the bottom graph, we have, so each edge comes with an direction. So for example, here we have this edge going from node 1 to node 2. So, and also for this edge, we have it from going from node 1 to node 4. So then we call this kind of graph undirected graph, because the edges are undirected. Whereas we call this type of the graph as directed graph, because the edges their directions associated with the edges. Okay, so does it make sense so far?
Yeah.
Okay, cool. So then to represent graph, we usually use this notation: G equals to V and E. So here V means the set of nodes or the set of vertices, and E means the set of edges. Okay, so we just separate the nodes with the edges. So that's why we have G, the graph G, as the combination of the vertices and the edges. So G equal to V and E. So this is how we denote a graph by using a mathematical way. And so there are a lot of applications of graph. So for example, if we so one famous application of the undirected graph is just the road network. So here in this graph, you can see that we have a lot of cities. This is the list of the cities in the United States, and then we basically can model each city with a node. So for example, we have this as Chicago, this as New York, and this as, for example, Philadelphia, and this as like Miami. No, not Miami. So this is, for example, Los Angeles. Okay, so here we can just use the edges to denote the road network between the cities. So for example, if there is a highway that connects LA with Chicago, so we build an edge between them, denoting that yes, from LA we can go to Chicago by using this road. So, but for example, if there is no direct road that connects LA with Philadelphia, then we don't build an edge between them. Make sense?
Yeah.
Yeah. Okay. Sure. So then this is the application of undirected graph. So is there any situation that you think that we will need to use a directed graph? So where the graph comes, where the edges are associated with directions. Okay, before that, let me give you another example. Okay, so for example, if you play Facebook, the social network, we usually model social network as a graph. So because we can model each account or each person with a node. Let's say this is me, this is another person, let's say you, and this is another person, let's say the, for example, I don't know, say my friend. Okay, this is just my friend, and so if you send me a friend invitation, so and I accept it, so then Facebook is going to build a link between us, denoting that we are friends. So so with this, we'll be able to see a graph to denote the friend relationship between different accounts of a social network like Facebook. Okay, so then can you think about a situation where we should use directed graph instead of undirected graph in the group?
Can you use it for like a GPS type thing?
So could you please explain that?
Like directions, which street is the quickest way to your route that you want to.
Okay, cool. So cool, great. So and so here we got one suggestion saying that if not here for different cities, again for the roads, okay, if we're not talking about the the road. We're talking about the traffic, say let's say from Philadelphia, if you want to go to New York City, you need to maybe spend 3 hours. But if you want to go from New York City to Philadelphia, it will only take you 2 hours because the traffic is relatively light. Yes, this is one good example. And here you can see that the reason why we associate an edge with the graph is because there are different meanings, or the different meanings associated with the edge for different directions. Okay, this is one good example. Is there any other situation that, for example, if we're talking about the social networks, is there a social network in which so we should use a directed graph to model, to represent?
What about like taking a plane to like a different country?
Take a plane to different countries. So I mean, so what do you want to, so you think it's going to be a directed graph, right?
Yeah, because like, you know how some countries you need to stop in like other countries to get to it.
Okay, yeah, cool. Yeah, I got you. So so here we got one example. It's like if we're talking about flights, for example, this is LA, and this is, for example, Tokyo. And so because of the COVID, and it's easy for to go from Los Angeles to go from Tokyo to Los Angeles, but if you can't, literally, it's very hard for to go from LA to Tokyo. This way, that the flight going from LA to Tokyo is very limited. So we can just kind of like eliminate that. So yes, that's a good way. Okay, cool. And here another example of the application of the directed graph is Twitter. So Twitter, so for example, if this is my account and this is your account, and this is someone like our previous president, I think that his account has already been eliminated, right?
Yeah, I think it's not there anymore.
Okay, so let's say let me use DT to represent it. So assume that it still exists. Let's say 1 year ago, his account still exists. So in the Twitter account, you may follow me. So if you follow me, then Twitter is going to build an edge from you to me, denoting that you're following me. And if I follow you, we're going to have the same thing. Okay, so Twitter is going to draw an edge from my account to your account. But if you look at here, okay, it's very natural for a lot of people to follow the president's account. Okay, so all of us, let's say both of us are following the president's account, but it's not very rarely the president is going to follow us back. So he probably will just ignore that. And and then there is no edge going from the president. There is no edge going from the president to us. So that's where we should also use a directed graph, because as long as the relationship is not mutual, we should use the directed graph. Make sense? Okay.
Yeah.
And okay, and let's come back here. Let's come back to the Facebook example, because if you send me a friend invitation and I accept it, I become your friends and you become my friends, and this relationship is just mutual. So we can just use a directed graph, sorry, undirected graph to represent the social network like Facebook. Okay, so this is the a brief introduction about the application of graphs. But say one example is here. Okay, so suppose here in a graph we have n nodes. If we get a graph with n nodes, how many edges can there be at most? What is the upper limit of the edges, of the number of edges?
Like 2 times n.
2 times n. So here 2 times n is, let me say, me put it this way. Okay, so for example, we build a graph like this. If we talk about 2 times n, so I understand your logic. Two means the direction, right? And n means the number of nodes, correct? But actually, it is more than that. So definitely it is more than that. The main reason is this. Okay, so let's say how many. Let's do a simple math problem. So if we're talking about an edge, there should be a source, SRC source, and a destination, DST. Okay, so if we are giving n nodes, so how many choices do we have for the source node?
Wouldn't it just be like the total number of nodes?
Yes, it's just n nodes, correct? So we can pick any node to be the source node, correct?
Yeah, correct.
So what about the number of destination nodes? How many nodes can we pick as the destination nodes?
Would there be 3?
Let's just be general. Use the number n to denote the number of edges, the variable n.
Is it n minus 1?
Okay, cool. Yes, it's n minus 1. So assuming that a node, so it's n minus 1 if we assume that there cannot be a situation like this, where we have a node that connects to itself. So can you see my screen with the example? Okay, maybe here, yes. Okay, so here you can see that for this node, it is connecting to itself, right?
Yeah.
Okay, so if we don't allow a node to connect to itself, then the number of choices for the destination nodes is n minus 1. But if we allow this node to connect to itself, so basically any node can also be the destination node, correct?
Yeah.
So we still have n choices. So let's say, and because these two things are the choice of source node and choice of destination nodes are independent. So we can just multiply the choice between them. So in total, we can have either this or this amount of edges. This is the upper bound of the edges. So if we have this number of edges, it means that we're going to have an edge between every pair of nodes. And then in that way, we got the maximum number of edges in the graph.
So n squared would be the amount of destinations you can have?
Not destinations. Here is the total. So the destination nodes, the number of choices of the destination nodes is either n minus 1 or n, whereas the number of source nodes is just n. So if we're talking about the maximum amount of edges, we need to multiply these two numbers, and so this is what we get.
Okay. So
yes. Okay, so this is the maximum amount of edges. So yes, and then the maximum amount of edges is this. So the number of edges is at most the square of the number of nodes.
So the most it could be is like v squared?
Yes.
Okay.
Make sense?
Yeah.
Yeah, makes sense.
Okay, cool. So then the next question that we want to discuss is that suppose that we have such a graph, how can we represent it by using a computer program? How are we going to represent such a graph by using the code? So there are two ways to do so. The first way is called adjacency list. So basically for each node, for each node, we're going to create a linked list which stores its neighbors. So for example, this node number 1, it has 2 neighbors, which are 2 and 5, correct?
Yeah.
Okay, so then for the node 1, we create a linked list with 2 nodes that are 2 and 5. So for node 2, what are the neighbors of node 2?
5, 1, 4, 3.
Yes, 1, 5, 4, 3. All the other 4, 4, 3. So all the other nodes are the neighbors of 2. So then for node 2, we just create a linked list which stores 1, 5, 3, and 4. So and then for node 3, okay, what are the neighbors of node 3?
So how do you know like the order of where to put them inside the linked list?
It doesn't matter.
Doesn't matter.
Just, as long as you store all the neighbors, the order does not matter at all.
So for 3, it would be 2 and 4.
Yes. So the neighbors of the node 3 is just 2 and 4. So here for the node 3, we just create a linked list with 2 and 4 inside it. Okay. So basically, in the adjacency list, the representation is to create a linked list of neighbors for every node. Make sense?
Yeah.
Yeah.
Okay. So then the other way to represent it, which is easier, and it is to create an adjacency matrix or 2D array, 2-dimensional array. So the point is that if we're giving a set of nodes V, and then we're going to create a matrix whose dimension is V by V, the number of nodes by the number of nodes. And so if there is an edge that connects any 2 nodes, we're just going to set the corresponding cell of the matrix as 1. Otherwise, we just denote it as 0. So for example, here in this example, we have 5 nodes, correct?
Yeah.
Yep.
Yeah. We're going to create a 5 by 5 matrix over here, or 5 by 5 array over here. So then this is pretty much like the example we show in the LCS. So each row represents something and each column represents something. Okay, so basically each row and each column is going to represent a certain node. So for example, here we have an edge from node 1 to node 2. So then we're going to set A12 as 1 and also A21 as 1. It means that there is an edge going from 1 to 2, and also there is an edge going from 2 to 1. And next, let's say, okay, here, is there an edge from 1 to 3?
No, no edge.
No. So then the cell 1 and 3, which is over here, is 0. And also because there is no edge going from 3 to 1, so A31 is also 0. Same here, because there is no edge going from there is no edge to connect 1 and 4. So A14 is 0. A41 is also 0. A41 is also 0. And since there is an edge that connects 1 to 5, so A15 is 1, and A51 is also 1. Make sense?
Yeah.
Okay. So basically, we're going to use each row and each column to represent a node. If there is an edge that connects these 2 nodes, we're going to set the corresponding cell of the matrix as 1. Okay, and then let's look at the example of a directed graph. So okay, before that, let's say if we fold the matrix along this line, along this diagonal, do you find anything interesting? If we fold it like this way,
Is it symmetric?
yes, it is. It is symmetric. Yes, because say here, this place is the same as this place. This place is also the same as this place. So basically, if you fold it along this diagonal, they're going to be exactly the same. So we call it symmetric. So is it a by accident, by some luck, or it has to be this way? Does it have to be symmetric?
I think it has to be symmetric because it's not directional, right?
Right. Excellent. So since this is an undirected graph, so if there is an edge connecting a node I to J, so we definitely can go from I to J. Similarly, we can go from J to I. So in that way, we will have A and J and AJI become 1. Both of them are going to be 1. So that's why we have this matrix as symmetric. Make sense?
That makes sense. Yeah.
Okay, cool. And so let's look at the example, this example of an directed graph. So from node 1, so here we have 6 nodes. So we create a 6 by 6 matrix. So from node 1 to node 2, there is an edge. So we put C12 as 1, denoting that there is a way to go from node 1 to node 2. But since there is no edge going from 2 to 1, so we have C21 as 0, meaning that there is no way to go from the node 2 to node 1. Okay, so is this matrix symmetric?
No.
No, right, because for directed graph, if you have an edge from node I to node J, it is not necessary to have another edge from J to I. Because the relationship is not mutual. So it's not the adjacency matrix does not have to be symmetric. Okay, so yes, this is the representation that we're going to use, and so we're going to use this representation throughout all the homeworks because it's easier. You don't have to create the linked list. Instead, you just specify, you just use a 2-dimensional array, and which saves a lot of efforts when you just create this graph by using your program. So here, let me say, okay, if I give you such an adjacency matrix, let's say, if I give you such an adjacency matrix, I want you to find the neighbors of 3, of node 3. How are you going to find it? By just looking at this array, this two-dimensional array. How are you going to find the neighbors of the node 3?
Whichever column doesn't have 0 in it.
Right, cool. So basically you go to row 3 and check which column does not have a 0. So this is not a 0 and this is a 0. So then you find the index of those non-zero cells, so which are 2 and 4. So this means that the neighbors of 3 is 2 and 4. So let's go back to the graph. So the neighbors of 3 is 2 and 4, right?
Yep.
Yeah.
Okay. So this is how you look for the neighbors of such a node. You just go to the corresponding row of the matrix and find the index of the non-zero cells. Is this simple?
Yeah, it makes sense.
Okay.
Yeah.
So you're going to use this in your homework. So okay. So okay. So any questions so far?
Not for me.
So if you have any questions so far, just ask it. I'm going to. So otherwise, I'm just going to proceed to the breadth first search algorithm. No? Okay, so then I'm going to discuss the first search algorithm. It is called breadth first search. The breadth first search takes two input parameters, arguments. The first one is just the graph G, which has a set of vertices and a set of edges, and then a source node. So S is a node inside this graph, and the output. So we want the output to be the so the set of destination nodes that are reachable from the source, and also we wanted to tell us what is the minimum distance from source node to this node. So basically, so for example, if we are giving such a graph, and we say this is the source node S, we say Frank, this is the source node. We want this algorithm to output the minimum distance from the source node to every other node in the graph. Okay, again, we want it to the breadth first search algorithm is going to output the minimum distance from the source node to every other node in the graph. So for example, so by checking all the possible routes from the source node Frankfurt to, let's say, to Munich. So I'm not German, so I'm just, maybe we call it Munich or whatever. So this way it is going to be 85 plus 80, 85 plus 80 plus 250 plus 84. Let me say. So this way is going to be this distance. Which is 494. Correct me if I'm wrong. So I just calculate by right away. And if we follow this way, so it is going to be 217 plus 103 plus 167. So it's going to be 487. And if we go this way, so these are all the possible three ways to go. So it's going to be 173 plus 502. So it is going to be 475. Okay, and we find, okay, this is the best route. So it is going to tell us, okay, the best so the minimum distance to go from the source node Frankfurt to Munich is 487. So this is what we want the output to be. And similarly, it will output the minimum distance from the source to every other node in the graph. Okay. So do you have any question with the output of the breadth first search algorithm?
So this algorithm will show you all three, like all the outcomes or all the possibilities, and which one's the best, or just the best?
Just the best.
Just the best. Okay.
Yes.
This is how like Google Maps works.
No, not exactly. I'm going to talk about, this is a simplified version of the Google Map algorithm. We're going to learn how does Google Map work in 2 weeks.
Okay.
Okay. So So then let's look at the pseudocode. So as we said that the breadth first search algorithm takes two parameters, the graph G and the source node S. So for each vertex, for each node U belongs to G dot V minus S. So first, do you know what does this mean? What does this mean?
An element.
It's an element.
Yes, it's an element. It's an element of. It's the element of all the nodes. G dot V means the set of nodes, all the nodes inside the graph, except for minus S means all the nodes except for the source node. For all the nodes except for the source node, it is going to associate them with a color that is white, and a D that is infinity, and a pi that is nil. Okay, so then and then for the source node, it's going to give it a gray color, 0D and a pi, which is and also a nil pi. So here, guess what does color, and so color is easier to understand. Okay, what about what does D and pi mean?
Is it the distance?
Yes. So for each node V, the V dot D means the minimum distance from the source node to it. Okay, and V dot pi means this, the parent node of V to reach S. So so how to say that? Okay, suppose okay, I give you an example. Suppose this is your home, and so this is your source node, okay, which is your home. You want to go to your destination node, let's say our campus, MSU, and then suppose that you're using Google Map, and Google Map suggests this road for you. Let's say from your home, it asks you to first go to a place, let's say Natalie, and then go to Clifton, and then go to, let's say here is Little Far. Okay, so then Google Map shows you, okay, this is the best route, and then for this node MSU, we say its parent is going to be Little Far. Its parent is Little Far. The reason is that in the shortest path from the source to this node, we need, so the node before this node before MSU is just Little Far. So the parent is like which node you need to visit right before the destination. Is that clear?
Yeah.
Okay. Okay. So the parent means so for any destination, its parent means what is the last in the shortest route. What is the last road right before the destination? So here our destination is more clear. So in the shortest path, the last node before it is just Little Far. So we say, okay, its parent is Little Far. Make sense?
Yeah.
Okay. So so here, if you're not sure what does parent means so far, no problem. It will be very clear at the end of our lecture. And then we associate each node with a color. So the color can be either white or gray or black. If the color is white, it means that this node has not been discovered yet. It's a piece of white paper for us. We have no idea about it. If it's gray, it means that we have already visited this node, but not all of its neighbor nodes. If the node is in the black color, it means that both this node and all of its neighbors have been thoroughly visited. So we will not visit them again. Okay, so this is the meaning of the three colors. White, again, white means not visited yet. Gray means we visited this node, but not all of its neighbors. Black means that we finished visiting both this node and all of its neighbors. Okay, so this is the application. So the meaning for these colors. So here you can see that we associate a gray color for the source node, and we associate 0 distance for it, and we say its parent is nil, means does not exist. And then we have Q equal to this. What does this mean? What does this mean? Mathematically, what does this mean? It means empty set. We're creating an empty set. And here you can see that we have Q, and then we have some operations like InQ and DQ. Okay, so is there any data structure that you can relate these 2 operations to?
Yeah, the Q.
Yes. Okay, so here, great. This is this is a Q. This is a Q. We are creating so Q is basically a Q. And initially we created an empty Q, a Q that does not include any element. So it is empty. So this is what does this line mean. Okay, we created an empty Q. And then next, we InQ the source node. We insert the source node to the Q. So, and while the Q is, what does this mean?
It's not an empty set.
Great. It means that this Q is not empty. Q is not empty. While the Q is not empty, so we DQ. It means that we remove an element from the Q. What kind of policy does Q implement? Which element are we going to DQ?
First in, first out.
Yes, first in, first out. So the element that we DQ should be the element which enters the queue first. Great. And next, for each node V, that is an element of G.ADJU. Okay, so G.ADJU, guess what does this mean?
It's an adjacent node. If it's like an adjacent.
The neighbors or adjacent nodes of the neighbors of U. Okay, for each node V, that is a neighbor of U in this graph. If its color is white, we associate it with a gray color. We change the color to gray, and we set its distance as U dot distance plus 1, and then we set the parent of V as U, and then we InQ it. So we InQ V into the Q. And finally, we after we finish the for loop, we're going to change the color of U to black. Okay, so this is the pseudocode. And so let me explain it now with an example. Okay, so this is the first part of the pseudocode. I'm going to pull up an example over here. Okay, so we have such a graph G. So okay, so this is the set of graph. Let me use a different alphabet to denote that. Okay, so okay, let's do not call them let's call them A, B, C, D. Okay, so we have these 8 nodes, a graph with these 8 nodes. Is the graph directed or undirected?
Directed.
No, it's undirected because there is no direction associated with the edge. So this is an undirected graph with 8 nodes. Okay, so let's start. And so, for example, here we're going to set S as B. So this is our source node is right over here. This is our source node. Okay, this is our source node S. Okay, so we basically want to find the minimal distance from this node to all the other nodes in the graph. Here, I think there is a match between these 2 nodes. Okay, so let's say first for U belongs to G dot V minus S. What is G dot V? What is G dot V?
It's the graph nodes.
No, G dot V means all the nodes in the graph, so which includes A, B, C, D, E, F, G, H. Okay, so this is G dot V, and minus S, if we let it minus S, it will be, so here we have S as B, correct? The source node is B. So it's like we are going to eliminate B from this side. So then we got this set as A, C, D, E, F, G, H, correct? Am I correct?
Yeah.
Okay, so for each node that belongs to this side, so basically we're going to use U to iterate through all the nodes over here. So firstly, we have U as A. So U is here, we have U as A, so we're going to associate this node A with an infinity distance, a white color, and neo parent. So we're going to put them over here. I'm going to give them an infinity distance, white color, and neo distance. And then, so here we just finished the iteration at A. So next we're going to go through the iteration at C. So we're going to give C these things: infinity distance, white color, and a neo distance. And then it is D. So basically we're going to do this for all the other nodes in the graph except for the source node.
Wait, so
Okay.
why do we set the color to like white?
Sorry?
Why do we set the color to white?
Because if you remember, okay, white means that we have not discovered this node yet. So because we haven't started the search yet, so we give all the other nodes with a white color.
Okay.
Okay. And next, so here we just finished the for loop. And next we have s dot color equal to gray. So we're going to give the source node, which is B, gray color. So we're going to give it a color that is gray, and its distance is going to be 0, and its parent is also neo. So it has 0 distance, gray color, and neo parent. Okay. So why do we give it 0 distance?
Because that's the starting point. That's the source.
Yes. So let me ask you one question. Okay, what is the minimum distance from your home to your home?
0. Well, down
Yes.
here.
Same here. What is the minimum distance from the source node to the source node? Automatically it's 0, right? You don't need to move your foot. Correct?
Yeah.
Okay. Okay. So we give it a color gray. It's like we are sitting at this source node, and we just visited this source node, and we're going to explore all the other nodes to see what is the minimum distance to the other nodes. Okay. So that is what we mean over here. The next, we create a queue that is empty initially. So we create a queue that is empty initially, and then now we in-queue. We add one element to the queue. So the queue, which is S, so the queue has one element because the source node is B. So the queue has one element that is B. Correct?
Yeah.
Okay. So this is the result of the first part of the algorithm. We just associate each node with a color, distance, and parent, and we create a queue with the source node in it. So, any questions so far? No? Okay, so then I'm going to continue. While Q is not empty, we have U equal to DQ. Okay, so this is the second part of the algorithm. So first, let's check while the queue is not empty, is this queue empty or not?
No, it's B.
Yes, so it has one node, so it's not empty. So we are able to execute the next line. We have U equal to DQQ. So what is U now? Which element are we going to DQ?
B.
Yes, this B is going to be gone, and we have U equal to B. So we put U at here. So U and S are the same node now. Okay, for each node V that is adjacent to U. So okay, tell me what are the neighbors of this node? What are the neighbors of this node? Say it again.
A and F.
Yes, A and F. So it has two neighbors, A and F. So let's have its neighbors as A and F. Okay, for each V that is inside this node. Okay, so first we have U equal to V equal to A. Let's put V over here. Let's put V over here. V as A. What is the color of V?
It's white.
Yes, it's white. So this is true, correct?
Yep, true.
Yeah.
Okay, so then we can execute the next few lines. So what we do is that we're going to change its color to gray. And so the reason why we change the color to gray is like, it's the first time we visit this node. So if this if a node is in gray color, it means that this node has been discovered, but not its neighbors. So that's why we change the color to gray. And next, we set its distance as u dot d plus 1. So here, u dot d is 0. So its distance is 0 plus 1. So it is going to be 1. Correct?
Yeah.
And then we're going to set its parent to u, which is b. So we are going to give it a parent as b. Correct? And then we're going to include v into the queue. So now the queue has one more element, that is a. So we finish this if statement, correct?
Yeah.
Are you with me?
Yeah.
Okay. So any question? No? Okay, if no question, then let's go. Then next so after finish this line, where should we go next?
You break out of the if statement.
If statement?
You break out of it, like you.
Yes, we go back to for. Yes, we just finished one iteration. We just finished the iteration at A. Now we're moving V. We're setting V to the next node, which is F. So we put V over here. Oh, sorry, it's the wrong one. Put V over here, and so again we're going to repeat these operations. What is the color of V?
White.
White. So we are going to repeat the previous operations. So we're going to set its color to gray, and we are going to set its distance as u dot d plus 1. So u dot d is 0, plus 1 is 1. So its distance is 1. And then we're going to set its parent to u, which is b. Okay. And then we're going to include it. So f is going to be in the Q2. Okay. Right. So now we finished this if. So we've also finished this iteration of the for loop. So when we go back to the for loop, we say, okay, we finished all the iterations of the for loop. So then we're done with the for loop. And which line should we go to next? What is the next line to be executed?
The u dot color equals black.
Yes, because we just finished the for loop. So we go over here. We set u dot color as black. U is here, so we change its color from gray to black. The reason why we change its color from gray to black is that now we not only finish visiting this node, but all of its neighbors. So according to the definition of the colors, we turn the node's color to black if both of this node and its neighbors have been discovered. So yes, that's why we set its color to black. Okay, so then we finish one iteration of the while loop, and then we go back to the while loop. We check if the queue is empty or not. It's not empty. So then we're going to do the dequeue work. So which node are we going to dequeue next? Which one?
We do A.
Yes, because A enters the queue first. So A is gone. So we have U equal to A. We put U over here. And for each V that is adjacent to U, which is A, what are the neighbors of A?
It's just like E and B.
Yes, B and E. So B and E. Let's say E and B. Okay. So first we have V as E. So we have V as E. We put V over here. What is the color of E?
It's white.
Yes, it's white. So this is true. We can execute the next few lines. What we do is that we set its color to gray, and then we set its distance as u dot d plus 1. Here u dot d is 1. So 1 plus 1 is 2. And we set its parent to u, which is a. So, and then we're going to do the enqueue work. Okay, put it in the queue, right? Am I correct?
Yeah. Yep.
Okay. So we finish one iteration of the for loop, and then we go back to the other iteration of the for loop. Next, we have v as b. Okay. So what is the color of b?
It's black.
It's black. So this condition fails. So we're not going to execute the next 4 lines. So basically, we are not going to do anything in this iteration, and then we finish the for loop. And so we go to the last line and execute u dot color as black. So u dot color is black. We are going to change this node's color to black. Okay. So then we go back to the while loop. So the queue is not empty. Still, it's not empty. So we're going to dequeue. So which node are we going to dequeue?
F.
Yes. So what are the neighbors of F? This is U. What are the neighbors of F?
B, C, and G.
Yes, it has B, C, and G. And according to the previous iteration, and you can see that we can totally ignore the neighbors whose color is not white, because we're not going to do anything. We're not going to be able to execute these 4 lines. So we can skip the node B because its color is not white. So then we just need to so focus on C and G. So let's say first we got V as the first node C. Okay, so its color is white. So what we do is that we're going to change its color to gray and assign its distance as u dot d plus 1. What is u dot d? What is u dot d? Say it. It's 1, right? U is F. This is U. Its distance is 1. So it's going to be 1 plus 1, correct?
Oh, yeah. Correct.
Okay, so it's 2. And then we're going to set its parent to U. V dot pi is U. So we're going to set its parent to U, which is F. And then we're going to enqueue it. Sorry, this node is F is gone. So we're going to enqueue it. So, okay. And so we finish this iteration, and next we will start the iteration at G. So we have V as G over here. And again, we're going to do the same thing for it. We're going to set is, we're going to repeat these operations and put it and append it to the queue, insert it into the queue. Okay. So this is what we do with these 2 nodes. And then we finish the for loop, and then we are going to execute the last line by assigning the color of U to black. Okay, so it is black. So next we go to the while loop, check if the queue is empty or not. It's not empty, right? The queue is not empty. Am I correct?
Correct. It's not empty.
Yes. So we are going to pop up E. So E is gone. And we have U as E. What are the neighbors of E?
Just A.
Just A. But the color of A is not white, so we're not going to do anything with it. So we can totally ignore that iteration, and then just go to the last line by assigning its color to black. Okay. So E is gone. So next we go back to the while loop, and then we have C over here. So we're going to, sorry, C is already gone. So then we have G. Oh, no, sorry, C is over there. C is over there. G was gone. So the next node that we're going to pop up is just C. So we have U over here, and so then so what are the neighbors of this node?
F, G, and D.
F, G, and D, but among them only only D's color is white. So we're only going to focus on D. Okay, do some work for D. So what we do is that, okay, we're going to change this color to, we execute this line by setting its color to gray, and then next we're going to set its distance to u dot d plus 1. U dot d is 2. So now this distance is 3. And we're going to set the parent of d as u, which is C. Okay. So this is what we do. And then we're going to enqueue it. Okay, we're going to enqueue d to the queue. So okay, so and then at last we're going to change the color of u to black. Black. It's just F. Its parent is just F. Okay. So so next we are going to going back to the while loop. The queue is not empty, and so we're going to dequeue. The node that we dequeue is G. So what are the neighbors of G?
F, C, and D, and H.
F, C, D, H, but all among them only H is white. So we're only going to focus on H, the node H. And then what we do is that we change its color to gray, and then we set its distance as the distance of G plus 1, which is 2 plus 1 and 3. And then we set its parent to we set its parent to G. Sorry, the G's parent should be F. Should also be F. I made a mistake over here. Okay. So then and then we enqueue it. Okay. So then we're going to change the color of U to black. So then we just continue, and the last 2 iterations is like we are going to change the color of D and H to black and dequeue them. So I don't have the time to go through the detailed steps, but the result is that we are basically going to change its color to black, and then so everything else would remain the same as what we have over here. Okay, so yes, then in the end the queue is empty, so we terminate. So that's the result when we terminate the program. And remember, could you please recall what is the expected result of BFS? Do you remember what is the result of BFS?
I think it's the fastest way to get to the source.
Yes, the minimum distance from the minimum distance from the source node to every other node in the graph. Okay, here if I ask you, okay, what is the minimum distance from the source node B to C?
Three.
No,
No.
the number is here, 2.
Oh, but so wouldn't you go to F and then C though? Or no, would you
Sorry?
just go straight to B to C?
So, okay, so your question is that how could we get the distance 2, right?
Yeah.
Okay, so by following the parent, before C, we need to go to C's parent, which is F.
Uh-huh.
And when we reach F, we need to go to F's parent, which is B. When we reach B, we need to go to B's parent, which is new, which means the beginning of, this is already the beginning of the route. So this route gives us the minimum distance.
Oh, so that gives you, okay, so 2 would be what you would take away from that. Like,
Yes.
So 2, all right, because I was thinking you would add 2 plus the F, so it'd be 3 technically.
Okay.
Okay.
Let's check another answer. Okay, what is the mean distance from the source to H?
Three.
Yes. Okay, and what is the route, that shortest route that gives us 3? From H, we need to go to its parent F. So no, its parent is not F. I made a mistake. Its parent should be G. Its parent should be G. So we should go to its parent first, which is G. And from G, we need to go to G's parent, which is F. From F, we need to go to F's parent, which is B. So this pink route gives us the shortest distance from S to H, which is 3. Make sense?
Yes.
Yeah, it makes sense.
Yeah.
Okay. So this is the output of the algorithm. And so so you can find the minimum distance from, for each node V, you can find the minimum distance with V dot D, which is what we show over here. Okay. Okay, so any questions for the BFS?
No questions.
No questions? Okay, so then so the last thing that I want to discuss is that the complexity is V plus E. You just need to remember it. So V is the number of nodes and E is the number of edges. This is because each node and each edge will only be visited at most once. So this is the last thing that I want you to know. Okay, so yes, this is the whole lecture today, and we have very tight schedule today. I'm glad that I finished this on time and just on time, and don't delay you. Okay, so then if you have question, ask it. Otherwise, that's the end of our lecture today.
I actually have a question.
Sure.
That was an undirected tree, or it was undirected, right?
Yes, undirected.
So for a directed graph, would you have multiple parents then?
No, just one
No,
parent.
just one.
Each node can only have one parent.
But I thought for a directed, you can have different ways of getting to a certain node, though. Can't you have 2 ways to getting to a node?
Yes, yes. We just need to know one of the way, one of the shortest way. So there could be multiple routes that gives us the minimum distance, but as long as we find one of them, it is fine.
But okay, so then the one that would be the parent would be the fastest way. So
yes.
So even though it can have 2 different ways to get up to it, the one that is the parent would be considered the fastest.
Yes.
Okay.
It always, if you follow the parent to find the route, you will always end up with the shortest route.
Okay. I was confused about that for the direct. I thought it would have 2 parents.
No, just one parent.
Thank you.
No problem. Any other question for me? Okay, So if no, then that's the end of our lecture today. So yes, have a good day.
You too, Professor. Thank you.
Have a good day, Professor.
See you, Professor.
Thank you.
Professor,
Hey.
I have a question about a homework grade that I got for last homework assignment. I got a 50 out of 100. And the only note that was left was that there was a compilation error for number 3, but number 3 was only worth 20 points.
Okay.
Wondering.
Sure. So can you send an email to me so that I can check it by myself? It's the GA who graded yours. So I'm going to check it.
Okay, thank you.
No problem.
Hey, Professor, I actually have a question, but not outside of schoolwork. So I was actually learning about the Blossom Garden because my girlfriend and I, or the cherry blossom manure, my girlfriend and I were actually to go this weekend. And I was like, oh no, it's not ready. Like, this is still early in the spring. So we didn't go. So is everything blossomed, or should we wait?
Yeah, I went there last Saturday. Everything is at the peak.
Yeah.
But
okay.
I think this week, if you go now, you should also be able to feel the most beautiful.
Oh, okay. I was telling her, I was like, why don't we just wait till May? Like, it'll be nice.
No. May is too late. It's too late.
Okay, so I'll tell her for this weekend. Thank you.
No
That's
problem.
funny that you went there, and I was like, hey, that's crazy. I was gonna go there this weekend.
Yeah.
All right. Have a good one. See you
You
Friday.
too. Bye.